So in this last unit, we'll look at some probability, and we'll talk about how we can calculate probabilities in different scenarios. So first, let's talk about what probability is. And it's defined as the likelihood of an event occurring. And you could, as I say here, you could be selecting the ace of spades, you could randomly select a sock out of your drawer, or it could be the probability of it raining tomorrow. Certain probabilities can't be calculated. For instance, the probability of a cat landing on its feet. Well, that's, I think, guaranteed. But in any case, you can't really calculate that. You just have to do an experiment over and over and over, 1,000 times or 10,000 times, however much data you want to collect. But certainly we can calculate probability in a lot of cases, and that's what we're going to study tonight. So we're going to take a look at recognizing that probability is all, the possibility of an event is called an outcome. And so, for instance, if we're rolling a die, then there are 6 outcomes. There are 6 possibilities. For drawing a card off of a deck, there are 52 possibilities, 52 outcomes. And so what happens here is that we will define probability as the number of ways to get success divided by the total number of outcomes, or the possible outcomes. Now this number of possible outcomes is called the sample space. And the way I want you to think about this number of ways to get success is, how many ways can I win this game? I always think of probability questions as a game. Step right up, roll a 7 and you win, or something to that effect. Now, probabilities will always be between 0 and 1, and that's because you have more possible outcomes than there are ways to have success. So the questions tonight come down to finding these two numbers. We either find this number or this number, or we find both and divide. And so let's take a look at how we can do that. So one of the ways that will help us to calculate these numbers is using tree diagrams or the fundamental counting theorem. And we'll do this with an example. So as university students, you have to take a language course, a math course, and a science course. There's 2 language courses, there's 3 math courses to choose from, and there's 2 science. And of course, as a true university student, you are randomly going to choose a schedule. So we want to figure out how many possibilities there are here, how many possible schedules. And what that really means is, what is the sample space? Now notice this is not talking about probability, so I'm not looking at the number of ways to get success. Okay, I'm simply talking about the number of possible outcomes here. So we can draw a tree diagram to help us with this. So the first course, what I can have here is an English or a French. And the second course, if I take an English, my second course could be stats, calculus, or algebra. In fact, if I chose French, those same courses apply here. And my third course, well, that can be either physics or geology. And so you can see how this branches out, which is why we call this a tree diagram. Okay, this is much like a family tree. But what this is showing here is the total sample space. So what I recognize is that here is a sample schedule. I could take English, calculus, and physics. Here's another one. I could take French, calculus, and geology. In fact, when I look at these and count these up, I see that there are 12 possible schedules. So, for instance, if you and I were randomly choosing these schedules, you might have one that's completely different than me, or you might have 2 courses that are the same and the third one's different. But there are 12 possible schedules in total. Another example where it's useful to draw a tree diagram might be to consider a family that has 3 children. What is the probability that the 2 youngest will be boys? So here I see the word probability, and as soon as I'm asking for probability, I'm looking at the number of ways to get success divided by the total number of outcomes. And so what happens here is that we can draw this tree diagram. Okay, if I have the first child, second child, third child, I always like to list out my options here, my stages, if you will, so that I can it helps me draw the tree diagram. So the first child here can be a boy or a girl. Second child, again, can be a boy or a girl. Third child can be a boy or a girl. And so what we see here is that there are 8 possible families. Now, I'm not finished. That's the sample space. But what I need to do here is I need to consider how many of these have the 2 youngest as boys. So that's the nice thing about the tree diagram, is that it actually shows me. Here, this family has the 2 youngest of being boys. So does this family. So what I can see is that there are the probability of having 3 kids, the 2 youngest of being boys, is 2 families out of the 8, or 1/4. Now I don't really care if you simplify those fractions or give that to me in a decimal. I'm totally okay with all that. Now these tree diagrams are very useful. But of course, if I ask you, about a family that has 15 kids, you don't want to be drawing that out. You don't want to be bringing a Bristol board into your exam to figure out these tree diagrams. So there's got to be a better way. So let's go back to example number 1 there, where we had to take these different courses. So I have this course 1, course 2, course 3. And I've got blanks here. And so what I see is that I had 2 choices for the first, 3 for the second, 2 for the third. And this equals 12. So of course what we can do with these numbers is we can multiply them out to get 12. 2 times 3 times 2 is 12. And this is called the fundamental counting theorem. In fact, I notice that I have it wrong up here now. This should be fundamental counting theorem. So what we have here is the way to quickly figure out the sample space. When we have a multi-staged event, this is what I call these, when you're picking more than one thing, or when you're having more than one kid, or when you're picking more than one course, or you're drawing a card and flipping a coin. When we have a multi-stage event, we can multiply the number of outcomes at each stage, and that will calculate the sample space. And my little hint here is if you're drawing blanks, draw blanks. So for instance, Subway said a few years ago that you could eat there for your entire life and not have the same meal twice. And that's pretty easy to do. Let's say you live to be 85 years old. So that's times 365. That would be how many days you lived. And then every day you have 3 meals a day. So a quick calculation here would roughly tell you how many meals you would have. So you'd have like 93,000 meals. Now notice I didn't talk about the price of 93,000 meals at Subway. But anyways, so how can we figure out how many meals are possible at Subway? Well, if I'm drawing blanks, I don't know where to start, I'm going to draw blanks. What I mean by that is I'm going to draw out the choices that I have to make. So for instance, the first one might be breads. Okay, so at Subway there might be, 5 breads. And then we have sizes of breads. So you have 6-inch, you have foot-long, you have so maybe you have 2 sizes. Then you have to choose your type of sandwich, so your meat. You can have a vegetarian, you can have, ham on it, chicken on it, whatever. So there might be 12 of those. Then you got to choose your veggies, and there might be 9 or 10 veggies. You got to choose your sauces, and there might be 10 sauces. You got to choose seasonings. There might be 4 or 5 seasonings. You also have to choose whether or not you have chips. There might be 7 or 8 different varieties of chips. you're going to have pop or a drink, so there might be, I don't know, 10 of those. And so what we can see here is that we have a multi-stage event. We have lots of choices to make. And so what we're going to end up doing here is, of course, multiplying these together. So when we multiply these, we'll figure out the total sample space. So just with our quick calculations, and this certainly doesn't account for all the different choices at Subway. I can't draw X's here. But just by multiplying these together, if I've done this correctly, we get like 30 million meals. Now, of course, you wouldn't want to be drawing out your tree diagram for this. So, by the way, if I'm only having 93,000 meals, if I divide the total number by the 93,000, you could live 328 full lifetimes and never have the same meal twice. Or another way to consider that is 328 people could live to be 85 and eat every meal at Subway, and they would never have a repeat, any of them. They would all have different meals every time. In any case, that's a quick way to multiply. It's called the fundamental counting theorem. Quick way to count, I should say, is to multiply. So let's take a look at practicing finding the sample space. I'm not asking about probability here. I'm simply asking how many total outcomes are there. So for question A, rolling a die, most dice have 6 sides, so there are just 6 possible outcomes here. Well, yeah, I'll just do this, I guess. Sorry about that. Question B, if I'm flipping 3 coins, so now I'm doing multiple steps here. I've got 1 coin, another coin, and another coin. I'm going to multiply those by 2. So this gives me 2 to the 3, or 8 different choices, 8 different possibilities. Drawing a card, well, there are 52 cards in the deck. Question D, drawing 2 cards. Well, now I'm doing 2 things. I'm going to multiply them. I have 52 choices for the first card, and I have 51 choices for the next. And so what we have here is 52 times 51 gives me 2652. In question E, now we have a slightly different scenario where we're still drawing 2 cards. I still have 52 choices for the first, but then I put it back, and then I have 52 choices, therefore, for the second one. And so what this would be is 2,704 choices. So again, that's just practicing finding the sample space, finding the total number of outcomes. Here's another example. If I have 3 shirts, 6 pants, and 4 pairs of shoes, how many random outfits can I create? So we're not asking, make sure that they match or that they are appropriate. Okay, this is just how most people, I think, choose their outfits. They just randomly put them together. Maybe it's not correct, but in any case, what we're going to do here is we're going to draw blanks. I've got 3 choices to make. For the first one, I've got 3 options. For the second one, I've got 6. And for the for the third one, I've got 4 options. I'm going to multiply those together. So that means that I have 72 outcomes, or 72 random outfits that I can make. Now, when we start talking about probability, the words and or become very important. The word and means that both events must occur. So if we have a game where you have to flip a coin and draw a card, to win this game you might flip heads and get a 7 of hearts. Well, you can tell just by thinking about that, that's going to be a very tough game to win. Whereas if it's or, it's still might be tough, but it's definitely not as tough, because if I win if one of those things happen. If both happen, well, that's great too. I win there. But if only one of them happens, I still win. So let's take a look at an example here. A pair of dice is rolled. What is the probability of? And now I've got all these questions here. But the first one is rolling a 6 on the first and a 5 on the second die. So again, because I see the probability, I'm looking at the number of ways to get success divided by the total number of outcomes. And so to win this, I must roll 2 numbers here, so there's 2 stages. Now, because it's probability, I'm going to draw the fraction. I definitely know that I have a fraction here. And now there's 2 blanks in each one. So I'm looking for the probability of rolling a 6 and a 5. Well, there are 6 options in both scenarios, and there's only one good one. There's only one way to get success for each stage. There's only one 6, and there's only one 5. And when I multiply these together, I multiply top by top and bottom by bottom, and therefore I get 1 over 36. Now question B is rolling a 3 on the first and rolling a 3 on the second. Well, again, this is the exact same question. And I highlight this because, you know, some people have this misconception that rolling a 6, for instance, is the hardest one to roll. That's not correct at all. On a fair die, rolling a pair of 6s and rolling a pair of 3s is the exact same probability. Now we roll an even number on the first and an even number on the second. So again, you see this word "and" here is important. And so I always like to write the probability out here as the probability of, and then I list the event here, the way to get success. So again, I'm drawing blanks. In my first stage, in my first part of the event, I'm looking to roll an even number. Well, there are 3 even numbers out of 6, and that's the same for the second die. And so when I multiply these together, this gives me 9 over 36, which reduces to 1/4. Now, let's introduce this word "or." So in question D, I can roll, to win this game, I can roll a 3 on the first and a 3 on the second, or I can roll 1 on the first and a 1 on the second. Well, right away, if you look at this, you've doubled your options to win. You have 2 ways to win now. You can roll a pair of 3s, or you can roll a pair of 1s. So it makes sense that my probability would be twice that of just rolling the pair of 3s. In fact, that's what we see here. What I'm going to do with the word "or," I'm going to add. So here's the probability of rolling the pair of 3s, as we discussed in question 2, I think it was. And here's the probability of rolling a pair of 1s. And it makes sense to add those because we know that we have twice the probability of just rolling a pair of 3s. We have 2 kind of chances to win here. And so the answer is 1 over 18. So what we see here is that the word "and" is going to tell us to multiply, and the word "or" tells us to add. But it gets a little bit more complicated than that, of course, right? So let's take a look here at a multi-stage event. A die is rolled and a card is randomly drawn from a deck. What is the probability of rolling a 6 and drawing a heart? Okay, that's what the first one we'll do. So again, because I'm dealing with probability, it's the number of ways to get success divided by the total number of outcomes. So I'm looking for the probability of rolling a 6 and a heart. Well, the word "and" tells me to multiply. So what I'm going to do is I'm going to take the probability of rolling a 6, which is 1 over 6. I'm going to multiply that by the probability of getting a heart. In case you didn't know, there are 4 suits in a deck of cards. There's hearts, there's diamonds. Oh, I didn't think about drawing these out. There's clubs, and then there's spades. And so each one has 13 cards in it. So 13 out of 52 is how many hearts there are, or 1 out of 4. That's the exact same fraction. So I'm going to multiply these top by top and bottom by bottom, reduce them first if you wish, and you get 1 over 24. By the way, you don't have to reduce the fractions for me. If this shows up on a multiple choice question, you just multiplied 1 by 13 and 6 by 52, you won't see your answer there. But what you could do is you would see your calculator would give you a decimal, and then you could check my 4 possibilities to see which one gives you the correct decimal that you had. There is also a button on certain calculators that is F to D, which means fraction to decimal. You can try and play around with that to see if you have that button on your calculator. There's also a button that looks like this, like A times B over C. Sometimes that works as well. It's not needed, but it might help you. Okay, so let's look at now the probability of rolling a 5 and drawing the 7 of clubs. This doesn't seem very likely, but again, I've got 2 events here. So I'm going to, and the word and tells me to multiply. So there are 1 out of 6 ways to roll a 5. There's 1 out of 52 ways to get the 7 of clubs. So when I multiply this together, I get 1 over 312, which again, not very likely. Now rolling a 6 or drawing a heart. This is now the word or. And we know that or means and. Nope, that's not right. We know that or means add, but let's consider this very carefully here. There are times where I would have rolled the 6 that I also would have picked the heart. And so if we're not careful, we're going to count those successes twice. Okay, so you can see here that that because we can roll a 6 and a heart, we've got to make sure that we don't double count those. For instance, rolling a 6 there's a probability of 1 over 6 of doing that. Or means to add, and drawing a heart is 13 out of 52. But some of the times that I rolled the 6, I would have also drawn the heart. Now I know that you could argue that no, once you rolled the 6, you wouldn't even pick up the heart because you already won the game. Let's consider that we're doing this at the exact same time. You randomly pick a card and roll the dice at the same time. So what we need to do is we need to make sure that we're only counting these once. And so what we're going to do is we're going to subtract the overlap. We're going to subtract the times where this happened, that both of these happened, I should say. And so the or questions become an and question as well. We're going to add and then subtract the multiplication. And so again, we can simplify this and we get 3 out of 8. So we have to be careful here. In general, what the equation is that we have is PA or B equals the probability of A plus, because it's the word or, the probability of B. But we have to subtract the times that they happen twice. And this is usually found PA times PB. Now I say usually this is when you have a multi-staged event. That's how you would find it. So a similar question is the probability of rolling an odd number or drawing a queen. Okay, so I see the word or. I'm going to look to add those probabilities, but then I have to subtract the times where they both happened. So the probability of rolling an odd number is 1/2, 3 out of 6. Probability of rolling a queen, there are 4 queens in the deck of 52 cards. Minus the probability of both happening, the and there means to multiply, so I'd multiply those fractions. Again, I can reduce those, and I can solve. And so there's a 7 over 13 chance of rolling an odd number and drawing a queen. Now this is slightly over half. And that makes sense because I win this game if I roll an odd number. Well, there's 50% of the time. Now I've also got this other chance of drawing the queen, which might not happen that often, as we see here. But that means that I was at 50% with just rolling the dice, or the die. Now I'm going to be slightly above that because I got this other chance to win as well. So our answer makes sense. All right, so let's take a closer look here. Consider an experiment where we pulled socks from a drawer. 7 socks are blue, 7 socks are white, and 9 are striped. This sounds like the drawers for my children because I used to think that socks came in pairs, but apparently now they don't. So you notice that all these are odd numbers. However, when we count up all the socks, we only see that there's 19 in the drawer. So how is this possible? Now, certainly, what could happen here is that some of the blue socks were also striped. And so when I told you that 7 were blue, I was counting these ones. And when I said 9 were striped, I was also counting these ones. So I counted socks like this twice. So what we'd have to do is we'd have to find out how many of those socks fit in more than one category. And so we counted them up, and let's say that there's 4 of the blue socks are also striped. So what we're going to use here is a Venn diagram to show all of this. So in a Venn diagram, what we have circles that will count as certain descriptors. For instance, here's our Venn diagram for this one. This circle, everything in this circle is a blue sock. So there needs to be 7 in that circle. Now, I see that 4 of the blue socks are striped. So those 4 are going to be in this blue circle, but they're also going to be in the striped circle. And so that's why there's an overlap here. Now, if 7 socks are blue, and I know that 4 of them are also striped, then there's 3 left over. And it says 9 socks are striped. Well, you already told me that 4 of them were blue as well. So there's 5 here. So you can see that there's the 9. And here's the 7. Now, this means that I have 12 socks accounted for. 12 socks are blue or striped. That means I have 7 that aren't, because I've got 19 in the drawer. And of course, these are the 7 that are white. So they're outside of those circles. One of the best examples I've seen of a Venn diagram, you can Google this. It's in one circle, like right here, you would have a beaver playing a guitar, and over on this side you have a duck playing a keyboard, and then the overlap you would have a platypus playing a keytar. If you're old enough to know what a keytar is, it's a combination of guitar and keyboard, and if you've ever thought of a platypus, it's obviously a combination of a beaver and a duck. So anyways, if that doesn't help you, then I'm not sure what will. Or maybe that made it more confusing. In any case, what we're looking at here is just separating the data to make it a little bit more clear of what exactly we have. Because if I just told you this information, 7 are blue, 7 are white, 7 or 9 are striped, you don't know how many are overlapped. Okay? So let's see how we can use this now. What's the probability of randomly picking one sock and it being a blue and a striped sock? So I'm only picking once here, so there's no multiplying. I'm just counting. How many socks are blue and striped? Well, that's 4 socks. Whoops. That's 4 socks, and so I've got 4 out of a possibility of 19 socks. If I look again here, blue or striped, again, I'm only counting once, so I'm only pulling once, so I'm going to count the number of ways to get success. So what I have here is the probability of getting the blue ones plus the striped minus both. So I'm going to show you kind of how this works. I don't think you would do it this way, but the probability of getting a blue one is 7 out of 19. And the probability of getting a striped one is 9 out of 19. And then the probability of getting the both, there's no multiplication here because I'm just pulling once. So this, I just count this up, and I would say I have to subtract those 4. So this gives me 12 out of 19. Now, I think obviously it's much easier here to just say, well, how many good ones are there? These are good, those are good, these are good. That's 12 out of 19. Okay, but I just wanted to show you this example to show you that this equation can work even if we're not technically calculating these and we're just counting them or just recording them. Okay, so that's an example of a Venn diagram and using the words and or. Now we're going to look at something a little bit different in terms of probability, and these are permutations and combinations. Okay, and so let's take, for instance, a question that you already might know how to do. Here we have a family of 5 that's asked to line up for a photo. How many ways are there to line up? So again, if I don't know where to start, if I'm drawing blanks, I'm going to draw blanks. I've got 5 people to line up. So the first person, I would have 5 choices. You know, the mom or the child or the baby could be here. Once I've picked that person, the second choice, I only have 4 left. And the third, I have 3, 2, and then 1. And of course, what I would do here is I'd multiply these together. Now, this one you can do in your head. This is 20 times 6. This is 120. Now, that's very easy to do. But if this was, you know, you were lining up 120 objects or, you know, 80 objects, this would be much more complicated. So what we have here is we have a new term, a new notation called factorials. Okay, and so this kind of taking a number and then multiplying it by every number down to 1 is a factorial. It's going to be very useful for permutations and combinations. So for instance, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. So the way that we write this is like this, and this is pronounced 6. No, sorry, that's the wrong way to read that explanation mark. It's just, you would say this is 6 factorial. So 10 factorial would equal 10 times 9 times 8 times 7 all the way down to 1. And this number is huge. In fact, you probably have this button on your calculator, and if you type in 10 and then hit this button, it's probably hidden somewhere. It's a second function kind of thing. But if you type in 10 and then this, you'll get 10 factorial, which is this. What is that, 3.6 million or something? So let's take a look at 12 factorial divided by 5 factorial. Well, 12 factorial is 12 all the way down to 1. 5 factorial is 5 all the way down to 1. And so what I can see here is that 5 divided by 5 is 1, 4, 3, 2, 1, 4, 3, 2, 1. They're going to divide to give me 1. So 12 factorial divided by 5 factorial is just 12 times 11 times 10 times 9 times 8 times 7 times 6, which gives me this huge number. Again, it's a good chance for you to maybe pause the video here and ask yourself, or sorry, try and find this on your calculator. If you're having trouble, I'm going to mention a few other buttons here tonight. If you're having trouble finding those, and you can kind of maybe take a screenshot of your calculator, maybe email that to me, and I can take a look and show you where these buttons are if you have them. Not every calculator has this, but I think it's pretty common now that they do. So what would be 14 times 13 times 12 times 11 in factorial notation? Now, by the way, it seems like we've taken a total break here from probability. We're going to come back and mix the factorials when we understand what scenarios they would be used for. We'll mix those with the probability questions, you know, and or, and things like that. The number of ways to get success divided by the total number of outcomes. So 14 times 13 times 12 times 11 kind of looks like 10 factorial, but we're missing, sorry, 14 factorial, but we're missing the 10 factorial. So it's simply 14 factorial over 10 factorial. Now the reason why we start using factorials is when we're picking a small group from a big group. When you see that, that's when you're going to start using these. So for instance, how many ways are there to randomly select 5 positions out of a group of 7 people? So here my small group is 5 and my big group is 7. And the word positions is important here because that means that the order in which I pick these people is important. For instance, the first person might be the president, the second might be the vice president, the third might be treasurer, the fourth might be secretary, and the fifth has to buy everybody lunch. So it really, you know, matters to you if you were picked in this group for one, but then even if you were picked first or second or third, that matters. That makes a difference. And so what we have here is, again, this is the exact same way we would do this normally. We would start drawing blanks. I've got 5 people to choose from. In the first person, I've got 7 choices. Then I've got 6. Then I've got 5, etc., etc. And so you can see that this looks like 7 factorial, except it's missing 2 factorial. So this is 7 factorial over 2 factorial. Now, the way we write this is 7p5. And the p here is because we have positions. We have order counting. So this is called a permutation. And when order is important, it's a permutation. So those combination locks that you use, you know, the ones that you spin the number and you have to get the 3 numbers in the correct order, those aren't combination locks. Those are actually permutation locks. But anyways, I don't think I'm going to be changing that anytime soon. I'm trying, but I think combinations is pretty stuck there. Anyways, let's take a look here. How many ways can I pick a president, vice president from a group of 3? So what we would have here is, if we have a group of 3, let's call them A, B, and C, I can pick the 2 people, or the president and VP. I'll draw a tree diagram here to show you, because that will show you the entire sample space. The president could be A, B, or C, and the vice president could be, in this case, BC, in this case, AC, in this case, AB. So there are all of the different ways. Yeah, sorry, I think that's, yeah, that's what I wanted to show you there. The way to write that would be 3 factorial. Or sorry, let me start again here. If I'm drawing blanks, let's draw blanks. So I have, and actually I only have 2 blanks. So I have 3 choices for this one and 2 choices for this one. So this is 3 factorial over 1 factorial. It's like impossible to draw a dot on this. There you go. So that's how I would get this. Now, when we use this notation, we can use NPR, where N is the big group and R is the small group. And so what happens here is that, you see, in our case, we would have 3 as the big group. We're picking 2 out of that. And so 3p2 gives us this value of 6. 3 factorial divided by 3 minus 2 factorial equals 6. And so, again, that factorial button makes these calculations easy. But what makes this even easier is the NPR button on your calculator. If you have a factorial button I can almost guarantee you have an NPR button. And so you can type in 3, then NPR, then 2, hit equals, and that'll give you 6. And that really makes your life easier. So let's do another example here. A group of 8 books must be arranged on a shelf. How many possible arrangements are there? So that a word arrangement tells me that order counts. Otherwise, it would just be one way, right? Otherwise, if order didn't count, it's like saying, how many ways can I put these 8 books, how many ways can I put 8 books in a huge box? Well, you just chuck them in one way. But here what we are doing is we're arranging them. Okay, so we're trying to put them in order. And so alphabetical order would be one way, reverse alphabetical order would be another way. It's all the same books, but there are 2 different ways, for instance. So let's take a look. Our big group is 8, and we're picking a small group of 8, and the order matters. So this is a permutation. So what I'm going to do is I'm going to have 8p8. If I go to my formula here, that's going to be 8 factorial over 8 minus 8 factorial is shown here. And 8 minus 8 is, of course, 0. And so 0 factorial is not something that makes sense in terms of our little definition of factorials. When I say 8 factorial, you're thinking 8 times 7 times 6 times 5 all the way down to 1. Well, I can't do that with 0 factorial. So we have to define 0 factorial as 1. If you type in 0 factorial into your calculator, it will give you the number 1. That has to be the case in order for our formula to work. So there are 40,320 ways to arrange 8 books on a shelf. And I just mentioned 2 of them, alphabetical order and reverse alphabetical order. But I could switch the first 2 books, have them in alphabetical order and switch the first 2, there's another one. Okay, so you can see that you wouldn't want to be drawing a tree diagram for any of this. Now, if order's not important, then we're going to use combinations. And with combinations, we still have n as the big group and r as the small group. But now what we have to do is we have to divide the number of repeats. And the number of repeats is going to be the small group r factorial. So for instance, how many ways can 2 people be picked from a group of 3? So again, this sounds like the question that we had before with the president and the vice president. But what I can do here is I can pick my first person to be A, B, or C. My second person can be B or C. I could have A or C here. I could have A or B. However, in this case, because it doesn't matter if you were picked second or first, this, A then B, is the same as B then A. There's a repeat. And AC is the same as CA. And of course, BC is the same as picking C then B. So really, there's not 6 ways, there's only 3 ways. So what we can see here is that when we have 3C2, so we would say 3 choose 2, instead of the pick. Permutations mean order counts. Combination means the order is not important, it doesn't count. What I would have here is the permutation, but then I'm going to divide that by the number of repeats. And I can see here that there are each choice had a corresponding choice that was a repeat. So A and B was a choice, but that's the same as B times A. So I really have to divide this by 2. Okay. So when I have a big group picking from a small group, I'm going to use permutations or combinations. If the order does not matter, then it's a combination. And again, you have an NCR button on your calculator. So let's take a look here. In a certain poker game, a player is dealt 5 cards. How many different possible hands are there? I'm not talking about probability here. This is just finding the total number of outcomes. So I have a big group of 52. I have a small group of 5, and the order doesn't matter. So this is a combination. And so I have 52C5. And so when I work this out, I get 2.6 million different hands. So I can now ask a probability question. What is the probability of getting a royal flush? And a royal flush means that you get ace through 10 in one suit. So that means there are 4 royal flushes, 1 for each suit. And there are 2.6 million possible outcomes. And so what we see here is that there's not much of a chance of getting the royal flush. Okay, I reduced that. Again, you don't have to. Now, we're going to take a look at this permanent combos and probability. This will be the last question we do, but there's a few different types of problems that I can ask about this. So let's consider a group of 7 women and 8 men, and a group of 6 must be chosen for a committee. So for a committee here, you're just on the committee or you're not. So the order doesn't matter. Okay, so we're looking at what's the probability that exactly 6 women are chosen. So I'm picturing 15 people, 7 women, 8 men in this room. I walk in and go, here are the numbers that I randomly picked. Seat number 2, seat number 4, seat number 7, seat number 2. I guess I said that already. Whatever. Those seats are going to be on, the people in those seats are going to be on the committee. So what's the probability that exactly 6 women are chosen? So what we notice here is, again, that we're dealing with probability. So we're going to use the total number of the number of ways to get success divided by the total number of outcomes. And we have a big group of 6. We have a small group of 6 from a big group of 15. That's what we're really doing here. But what you notice here is that I have to look at how many ways can I choose 6 women. That's how I get success in this scenario. Versus how many ways to choose 6 people. So if I'm looking at choosing 6 people, that's fairly easy. That's 15 choose 6. I've got a big group of 15 people. I'm choosing 6 of them. But now for the number of ways to get success, I'm going to look at just the women. So there are only 7 women. And so I'm going to have 7 choose 6 divided by 15 choose 6. And my calculator can do this very easily, and I get 1 over 715. Not very likely. I think this is the key here to be able to write out how you get this equation. Physically write out, okay, what is success here? Success is picking 6 women. And what am I doing in total here? I'm picking 6 people. So, question B, what's the probability of exactly 4 men being chosen? Well, remember, I've got to actually, again, small group from a big group, but remember, I've got to pick 6 people. So if I want exactly 4 men, that means I also want 2 women. So really this question becomes, what's the probability of 4 men and 2 women? And we know what this word and means. And means to multiply. So, how many ways can I pick 4 men? Well, again, what I'm looking at here is having a small group of 8 men, and I'm choosing 4 of them, and choosing out of 7 women, choosing 2 of them. And then the big group is still choosing 15. From 15, I'll choose 6. So my calculator will do this very quickly. I've done each individual part out, and I get 42 divided by 143. And you can give me the decimal form of that. And in terms of work shown, folks, all I need to see is this, and then that. And again, if you leave it like that, that's okay. Or if you put it in a decimal form, that's okay. But I need to see what you're calculating here. And I think to do that, you should be writing this down for sure. Okay, so here we have a group, the same scenario here. What is the probability that at most 2 men are chosen? So what does that mean? Well, how can I get success here? So that means I have to have at most 2 men. Well, that would mean that I could have 2 men and 4 women, or, there's an important word, I could have 1 man and 5 women, or I could have no men and 6 women. So let's take a look. I'm going to find the probability of 1 man and 5 women. Again, looking at the numerator here, I'm choosing 1 man out of a group of 8, and then I'm choosing 5 women out of a group of 7. So I'll have 8C1 times 7C5, or, which will end up being add, I can have 2 men and 4 women. So 8 choose 2 times 7C4. Again, divided by 15 choose 6, because that's what I'm doing in general here. Or I could have no men and 6 women. Now, how many ways can I choose no men out of 8 men? That's only one way. Hey, men, I'm not choosing any of you. That's the way that I can do it. So you can still type in 8C0, but you're going to get 1. And then I'm choosing 6 women, so out of 7, so that's 7 choose 6. And so what I would do now is I would add up all of these. And there's no subtracting here. If you recall, PA or B is equal to PA plus PB minus when they both happened. Well, what's happening here is that would be like saying I can have a committee with 0 men and 6 women, and at the same time that committee has 1 man and 5 women. And that's impossible. That can't happen. So there's no overlap here. And so I just add these values up. And so I get 3 out of 13. So when you have a big group and you're picking a small group, that's a combination. Your probability still counts in terms of, what and means and what or means. And so we can, pardon the pun here, we can combine those to make a combination of those to make kind of a harder question. So that's the course. I hope you learned it, or I hope you found it meaningful. I hope that it helps you in your future endeavors, and I hope you ace the final next week. Again, certainly feel free to post questions on the discussion board, and I'd also encourage you to practice with the homework and going over the PowerPoints and the workbook on your own. Okay, I guess that's me signing off for the last time, so take care and best of luck.